I guess it's 2 o'clock, so we can start. Yeah, it's a pleasure to introduce Martin Heirer, and he will speak to us on the role of symmetry in renormalization. Thank you.
Okay, thanks a lot. Thanks a lot to the organizers for that really nice event. So I want to focus sort of mainly on 2 examples. And so this is all based on joint work. It's essentially based on sort of 2 works. So one of them is joint with Lorenzo Zambotti from Paris, Eva, who's sitting somewhere in the room, and Frank Gabriel, who's now in Lyon, I think. And the second one is joint work with Hao, who unfortunately couldn't attend because of visa issues, as well as AJ and Ilya, who are both here. And so in both cases, this is about sort of a situation where, you have a singular stochastic PDE, which at least at the formal level exhibits some kind of symmetry. And then you ask yourself, well, if you want to give a meaning to that equation, then there's some renormalization involved. And then the question is there a choice of renormalization which is such that, the limiting object you end up constructing does indeed show the symmetries that you think it should have, right? So that's basically the general gist. And first, there's one sort of meta theorem, which, you can turn that into a theorem in various different contexts. And that basically says that if you can find a regularization that preserves the symmetries, preserves symmetry already exhibits, if you want the symmetry that you're interested in, then there exists a choice of renormalization, which also preserves the symmetry. I'm not going to, but also preserves the symmetry. And it may be, right, that in general, it might be, for example, let me give you one interesting kind of example in a second, which is one where at a sort of formal level, there are 2 different symmetries that you might want to have. And for each of them, you can find a regularization that exhibits, one of the 2 symmetries, but you can't find one that exhibits both at the same time. And there actually simply isn't any way of having a limiting object that has both symmetries at the same time. And that's the example that you're actually all familiar with, which is simply regular finite dimensional stochastic differential equations, right? Because if you look at SDEs, right, so just finite dimensional, so nothing fancy, right? So there's no SPD or anything like that. So you just look at the SDE, which is, like dx equal to whatever, f of x dt plus g of x dw. And x is in Rn, right? So it takes values in Rn. And the W is sort of like an m-dimensional linear process. Now, there are 2 sort of symmetries that you might want to have, right? So first, you can write that formally. You like to write this as a sort of controlled ODE, where this guy would be white noise. And of course, there's a problem of multiplying kind of white noise with the solution itself. So in a way, there's a bit of a question mark here of what that product actually means, right? So in the sense that here, there's a bit of a question mark of what that stochastic integral actually means. And so here, at a formal level, there are kind of 2 symmetries in that class of equations. So the first one is just the symmetry and the changes of variables, right? So you would say, well, if I write kind of y is equal to phi of x, and I just sort of pretend that the chain rule holds, then I can derive, if phi is invertible, right? If that's a diffeomorphism, then I can derive an SDE for y. And it's going to be of the same form with a different f and a different g, right? And so formally, I have somehow the group of diffeomorphisms in Rn that kind of acts on the space of pairs F and G, if you want, right? By just changes of coordinates. And so you can ask yourself, well, is there a way of sort of defining this that preserves that? And of course, here, what happens is if I simply mollify that noise, right? So I replace that guy by xi epsilon, where I just hit it with a mollifier, and then I try to send epsilon to 0, then one can find that there is actually a limit. There's no need for renormalization or anything, and there is a limit as epsilon goes to 0. And that gives you a solution theory, and that's what people usually call the Stratonovich solution, right? Where that's a Stratonovich integral, and that satisfies the chain rule, right? On the other hand, you have another sort of symmetry, which is that you would think here, because of the, so that's more of a symmetry in law, which is the fact that, you know, formally, white noise is sort of the Gaussian measure, which you, if you want to write this as a sort of path integral kind of formulation, right? It would be like an e to the minus 1/2 sort of L2 norm of xi square. And now formally times, you know, Lebesgue measure on the space of fields or whatever. And now formally here, well, since that's just an L2 norm square, you would think, well, I can multiply xi with anything which is in L2, and sorry, not with anything which is in L2, but I can multiply it with anything which preserves the L2 norm, right? So this guy is vector valued, so I can sort of multiply it with like an orthogonal matrix. And then it doesn't change that expression, and so it shouldn't change the law. And so that basically says that if I look at x dot, if I look at that equation here, and I look at the same equation with a g bar, sort of y times xi, and if I choose the g and the g bar in such a way that g times g transpose, right? That's a matrix valued guy because x is in Rn and w is in Rm, and so that guy takes values into matrices, n times m matrices. So if I look at g transpose, I choose the g bar so that, you know, this is true sort of pointwise for every argument. Then again, sort of formally, that means that I can write one of them as the other one times an orthogonal transformation, and the orthogonal transformation sort of hits the xi, and it shouldn't change the law of the xi, and therefore this guy and this guy should actually have the same law. And that's what we know under the name of E2 isometry, right? And because it's true also that you can find an approximation which satisfies this by, for example, I can like look at discrete time steps, right? So I can sort of discretize that in time. So instead of mollifying the noise, I can just view this as a sort of difference equation where sort of the dx is a delta x, and that's a delta t, and that's a delta w, right? And I just view this as a recurrence relation on Rn, and then I sort of send my delta t to 0 and ask myself if there's a limit, and there is a limit, and the limit gives you then what you would call the eta integral. And that one does indeed satisfy that property, right? But and the eta integral and the Stratonovich integral, they're kind of related by in the sense that you can add, if you write this equation in eta form and you add a term which is something like a half times the derivative of g times g, contracted in the correct way, which I never know what's the correct way. And I don't know if the plus is a plus or a minus, but you know, if you do it in the correct way, if you add this term here, then the solution to this equation interpreted in the eta sense is the same as the solution to, you know, this equation here interpreted in the Stratonovich sense. So they are kind of like the family of processes that you get is the same family, and they're just parametrized in a different way by the pairs f and g, if you want, right? But in principle here, you could sort of add an arbitrary constant instead of this constant a half, right? So you have this c, And in some sense, there's like a one parameter family of parametrizations here that are kind of natural, and they all show up naturally. If you come up with various exotic ways of discretizing this, you can basically come up with anything. You would always get the same family of limiting guys, and they would always be parametrized in essentially the same way, and the parametrization would always differ in some sense in the same way, but by a different constant, right? So it would not necessarily be a half, but it could be just any value you want by doing a bit exotic kind of approximations, right? So what this shows is that here, there's a way where, in some sense, at the formal level, there are two different symmetries that you could guess, but it's not possible to actually construct a limiting object that has both symmetries at the same time. Because I can find some approximations that have one of the symmetries, and then the limit has that symmetry, some approximation that have the other one, then the limit has the other one, but there is none that actually has both at the same time, and there simply isn't a parametrization here which has both symmetries simultaneously, right? Now, on the other hand, it's kind of interesting, is there's a sort of natural SPDE version of this where I just add space and I look at a sort of an SPDE of that form. So let me actually write the coordinates explicitly, because that's it's the one that Ivar mentioned in his talk, which has sort of a natural geometric interpretation. So you can imagine that there's a target manifold, and that you actually, instead of taking values in Rn, you can imagine that it actually takes values in some target manifolds. And then that's sort of the coordinates. You put yourself in some chart in the target or something, and then that's the coordinates there. And then the natural heat equation for this target manifold, or if you want the gradient flow for the Dirichlet energy functional, is given by the regular heat equation, but the regular heat equation is not covariant on the changes of coordinates. Like if you, well, for example, if I embed my manifold into Rn and I start with a U on the manifold, I evolve under the heat equation, it's not going to stay on the manifold, right? So you have to add a correction term, and that's the Christoffel symbols. And it comes with sort of a, so if you add this, if you look at this equation here with the Christoffel symbols, then that's a sort of nonlinear version of the heat equation, and that one does actually stay on the manifold. So that's the natural heat equation with values in the manifold. And then you can add noise to that, and then a natural way of adding the noise is to take a bunch of vector fields, sigma, say sigma I, and then I take just like independent space-time white noises, right? So that guy now is space-time white noise, and the I is now the index that in this, index is the components of that space-time white noise. That doesn't have a geometric meaning, was the alpha is sort of like the the index in the chart in the manifold, and so that's a very natural sort of class of equations, if you want. And again, you have exactly the same two symmetries that you can guess, right? So on the one hand, there's one symmetry, which is, again, change of coordinates in the target manifold, right? So you just take any diffeomorphism in the target manifold, it sort of shuffles your charts around, so it completely changes, if you want, the analytic expression of the Christoffel symbols and of these vector fields, but it should be somehow the same, should give you the same solution or the same object. It should be a geometric thing, right? And on the other hand, for exactly the same reason as before, you would think that there should be another sort of symmetry, which is that if I choose a different sigma here, I choose a bunch of vector fields sigma I bar, so that, exactly as here. So if like the sigma transpose is equal to sigma bar transpose, in the sense that I put like i's and i's, I and a sum over I, and I have like an alpha beta. Right, sort of like that's one way of writing it. So if this is true, then you would expect, the solution, the law of the solution at least, to be the same, again, by some form of E2 isometry, right? And as in the case of SDEs, like you can easily find a way of approximating this that preserves invariance or equivariance on the changes of coordinates, which is simply, hit the noise with a mollifier here. Right? So if I just hit that guy with a mollifier, I replace my psi by some psi epsilon, then that guy is smooth. It's simply a random PDE, chain rule holds, and so it's a geometric object. Right? No problem. And again, for this E2 isometry, one way of, for example, enforcing it is I can hit, instead of hitting the noise with a mollifier, I can interpret this as an E2 integral and hit the whole thing here with a mollifier, or even like the whole equation. Doesn't really make any difference. So I can hit this whole expression with a mollifier, interpret this as an E2 integral, then it does actually satisfy E2 isometry. And then again, I can ask myself, does it have a limit as epsilon goes to 0? Or maybe I have to renormalize in some sense. But in any case, can I do the renormalization in such a way that the limiting guy satisfies that E2 isometry, right? So in this particular case, you actually have the best of both worlds. Okay, so the theorem of the paper with Ivan, Lorenzo, and Frank says that there is a way of renormalizing that equation so that you get a solution theory which actually has both symmetries at the same time, even though you can't apply that meta theorem here. Right? So you're like, we haven't found any way of discretizing that in a natural way. So that one, we don't really have a good way of discretizing it in such a way that both symmetries are kind of satisfied for the discretization. Still, you can actually prove that there is a way of renormalizing so that both symmetries are satisfied in the limit, right? Although for the case of SDEs, they are not. Now, there's another example. So there are the two examples that I want to sort of focus on, right? So there's this one, and this one is the one that's sort of easiest to write down, and it has sort of a relatively straightforward kind of geometric interpretation. There's another example which is sort of probably of more interest for at least one half of the audience here. Just more of the QFT half of the audience, which is if you do the stochastic quantization of Young-Mills. Right? So if you take Young-Mills, and you can do a similar sort of thing in the sense that you have the Young-Mills energy, and then you look at the gradient steepest descent, if you want, the gradient flow for the Young-Mills energy, and you add noise to that, then that gives you sort of the stochastic quantization of Young-Mills. And then that should have a symmetry, which is gauge invariance. And there, it also turns out that there is, at least we don't know of any nice way of regularizing it that preserves gauge invariance. I mean, you can take lattice gauge theories or something, but then you're in trouble having to prove that it actually has a limit, right? So in 2 dimensions, there is recent work by Hao and Ilya that actually does that. And I think Ilya and Hao are both going to talk about it. I guess to some extent that already kind of more relies on the fact that one also knows how the continuum guy sort of behaves. So in the case of Young-Mills, there's also this natural symmetry, which is sort of gauge invariance. And so I want to actually focus on the example of Young-Mills, because even though it's not so obvious a priori what the equation is, and there is some sort of a slight subtlety in how to, when you derive it, it's a more interesting case from the point of view of these symmetries, because there's a kind of one single symmetry for which you don't have any approximation that preserves that symmetry. And still, hope that I be able to show somehow an argument that shows, how you can still prove that there is a way of constructing a limiting object which does preserve that symmetry, that gauge invariance property. And one thing which is nice is that in the case of Young-Mills, the potential counter terms in the renormalization procedure are simpler than in the case of that equation here. So here, in a way, if you sort of go through this whole machinery of regularity structures that builds solution theories to equations of that type, it basically tells you, well, if you mollify this guy, there's a bunch of counter terms that you can add, and they are all of the form, there's some sort of potentially diverging constant. These diverging constants are sort of indexed by some trees or some labeled trees with various decorations. And each of these come with some, f tau alpha of u, and these functions here, they are built out of the sigmas and the gammas, and there is a somewhat explicit procedure that tells you how to build them out of the sigmas and the gammas, but it quickly sort of becomes messy and so on. Whereas in the case of Young-Mills, it's more like 543 in the sense that renormalization is really just like a mass term, in the sense that, at the level of the equation, it's like a constant times a linear term in the solution, and that's it. And so there's only one constant that one can focus on. And then the question is, can you tune that constant in such a way that you actually have gauge invariance? Okay. So are there any questions so far? Yes. Sorry, if I
ignore the x-dependence in the thing that Brown motion.
Right.
Same thing that once you write it and then you know the part, you do it.
Yeah, so if I take Brownian motion on the manifold, then I'm not sure. I have to check. I mean, not sure. Yeah, but it's but in some sense, I mean, like here, it doesn't really make any difference whether you view this X as being in Rn or so. I mean, the thing is that here you end up, I mean, the way you end up viewing this is instead of you embed your manifold into some Rn anyway, and then you just view it as being in Rn, right? And then sort of one of the symmetry properties is that if these guys are Christoffel symbols for the embedded manifold and a vector field on the embedded manifold, and you start on the embedded manifold, you want to stay on it, right? But that's sort of not really different here, right? In the sense that here I could sort of just say, well, if that guy, if these two guys are sort of both vector, there's some embedded manifold in my Rn, and these guys are both sort of tangent vector fields that are tangent to that manifold, then you would want the solution to this equation to kind of stay on that manifold. If you start on it, then you're basically forced to choose Stratonovich integration, right? Sure. Whereas, okay, anyway. Okay, so Young-Mills. And here the interesting case is actually, from that point of view, the interesting case is 3 dimensions. And that's one can do the same thing in 2 dimensions, but one doesn't need this. So this whole argument I'm going to explain, you can actually reduce it to an explicit calculation in 2 dimensions, which is relatively easy to do. And so one doesn't really need that argument in 2 dimensions. So here, okay, I'm not going, since I only have 25 minutes left, so I'm not going to spend much time on the background of Young-Mills. So either you've heard about it or you haven't. I mean, I suppose at least half of the audience knows quite well about it, and maybe the other half doesn't.
Maybe for the other half.
Yes,
Gauge invariance.
right. So I'm going to, exactly. Okay. So gauge invariance is sort of the analog in that context of the changes of coordinates, right? So it's basically a kind of change of coordinates. But here the fields, so here you have an ambient, there's some compact Lie group, group G, which you can think of it as being just SON or something like that. And it has a Lie algebra, which is, it's usually a sort of Gothic G. Then that's a vector space, right? That guy's obviously not. And the fields here are essentially a one form with values in that Lie algebra. So you basically have AIs, so that AI of X or of XT takes values in G, and I goes from 1 to 3 because you're in 3 dimension, and X is on the, say, 3-dimensional torus. I don't want to deal with like large space. And here what one would call the gauge group. So the gauge group is the analog, if you want, of the group of diffeomorphisms here. So that would be functions G that go from your base space, so say the 3-dimensional torus, into that Lie group G. And if you want, you can think of it as being really somewhere at each point of the torus, there's a copy of G attached, and you sort of do rotations of these copies of G, but you don't move around in real space, right? So it's only in G space that you do a kind of change of coordinates. And now there's an action of that guy on these fields. And I just define it, and there's a reason why it's defined like that, because these guys have interpretation as a connection. And then if you take that interpretation, there's a natural way in which it transforms. And if you sort of go back and figure out what it actually does to these guys, what you find is it just conjugates them. But then it adds a term, I think it's with a minus sign. Yes. And here you just have like a DGG inverse. Okay, so it acts like this. You can check that this is an action. So this is a group by just pointwise multiplication. Okay, so that's the way in which you think of that as a group. And then that group acts on my space of one forms in this way. And there's a notion of curvature, which well, it doesn't really matter what the exact definition is, but it's essentially something like, this is a one form. You can take exterior derivatives, so that gives you a two form. And then you can add a term which is essentially the Lie bracket of A with itself, but that really means, the IJ component of that two form has the Lie bracket of AI with AJ. Okay, so this is not zero. It's not the same component here. And that, again, has a natural interpretation as a curvature. And the Young-Mills functional S of A is a half times the L2 norm of that guy, right? So integral of sort of FA of X squared dx. Okay, so that's Young-Mills. And the important thing here is that S of AG is equal to S of A, and that's the gauge symmetry. Okay, so the gauge invariance here is the fact that your energy functional has this invariance here under some big infinite dimensional group, right? So there's a big infinite dimensional group that acts on your field, and your energy functional is invariant under that action, right? Which means that necessarily even if you already look at just the gradient flow, it's not going to be terribly coercive, right? Because if you want your gradient flow to be nice, that sort of means you would want your action to kind of grow nicely in all directions. And here, of course, it's not, because there's going to be infinitely many directions in which it doesn't grow, because sort of along the orbits of that group, this guy is constant, so it doesn't grow, right? But the orbits of the group are, of course, non-compact because it's an infinite dimensional group, right? Or at least in general, you wouldn't expect them to be compact, and they're really not. So if you actually write down just the gradient flow for this, what you find, sort of the gradient flow, you find something like dTA, say AI, you get a Laplacian, which looks nice. But then you have a term which is a di dj aj. And then you have additional sort of nonlinear terms. And in some sense, the exact form of the nonlinear terms doesn't really matter for what I'm going to say. What matters is that it's somehow, there's a term which is essentially quadratic in, bilinear in A and its first order derivatives. And there's another term which is sort of trilinear in A. So it's like a cubic term, okay, which is essentially like a triple, like an iterated Lie bracket or so. So that's the sort of general structure of these terms. The point here is that because of this term here, this guy is not elliptic, okay, this operator, because this is really like an exterior derivative also, and the exterior derivative, it's like a D star D kind of operation. And you know that on one forms, D star D is not elliptic, but D star T plus DD star is elliptic, right? So this is only half of a Laplacian in that sense. So it's not elliptic. But this equation here formally has this gauge invariance in the sense that if I fix some G and I define AG in this way, and then I stuck it into this equation, then the precise way in which these terms are defined are such that, the whole thing sort of cancels out and AG satisfies exactly the same equation again, yeah, as you would expect. Now, on the other hand, physically, one only ever cares about observables that are themselves gauge invariant. So in some sense, we don't really care about A itself. We only care about its orbit under the gauge group. Like A and AG, we sort of think of them as actually being the same, just sort of viewed in two different ways. Okay? So one really only cares about gauge orbits. And that means that here I could add a term to this equation, provided that it doesn't change the gauge orbit that I lie on, right? And so you can think of, your space as being sort of foliated like that. And so here, you start with some A and then your solution does something. Here, what it says is if you start with AG, I run my solution. Here, I end up with some AT. This guy is precisely going to end up at ATG, right? In some sites, like applying this G operation and taking the time evolution are two operations that kind of commute, right? That's what we said here. But now what I could do is I could, for example, push that guy around a bit, right? If I push that guy a bit around, well, this basically tells me that it's still going, right? So if I push that guy around a little bit, it's going to end up here, which doesn't matter. It would still be on the same gauge orbit, right? So I can add to this equation anything that pushes me in a direction which is sort of parallel to the gauge orbits, and that doesn't change which orbit I end up in at time t, okay? Even though it changes which A I end up in at time t, but it doesn't change which sort of equivalence class I end up in if I consider these guys to be equivalent, okay? So what you can do is you can actually add here anything which is of the form some like covariant derivative of any zero form omega. And so it turns out that actually if I take the omega to be precisely the divergence of A, then that actually just cancel out this term. Okay, and somewhere, because it's a covariant derivative, it adds a term here, but it sort of doesn't really change the structure of the equation. All right, so actually I can just remove that term. And right, so if I do this, now the solution to this equation, what does the gauge invariance, what form does it take? Instead of, now it's no longer the case that if I start with AG and I flow, it's the same as just applying G to this. But it's still almost the case in the sense that I can derive an equation for G, which is such that if I apply GT here, now I have a T-dependent gauge transformation, then this picture still sort of commutes, right? So in the sense that if I start from AG, and then I run my evolution for time t, it's the same as first running the evolution and then applying a gauge transformation, but now it's no longer the same gauge transformation G, but it's the gauge transformation that was itself evolved in a suitable way, depending on, you know, the term that I added here in order to cancel that out, right? So you still have this kind of nice gauge symmetry here. And now what we want to make sense of is sort of the stochastic quantization of Young-Mills. So we want to sort of write down the Langevin equation such that the invariant measure would be the Young-Mills measure. So it's sort of like e to the minus Young-Mills energy functional. And that would be given by exactly this plus space-time white noise, right? So it's like, it's a sort of, you know, Lie algebra valued space-time white noise, and the different I components are just independent. Okay, so you have that SPD. And so now again, formally, if you do, you know, so sort of the formal calculation ends up a bit messy, but, you know, you can do the same sort of thing in the sense that you can look at AG, but now, again, the G, you want to evolve it in time. So you have some time evolution for the G. And then you want to say, well, if I start from A and I just run this equation here, then that should be basically the same as starting from AG and running the equation, but then applying to it, say I have that time-dependent gauge transformation, which is now a sort of random time-dependent gauge transformation. And the solution that I get by starting from AG should be the same as the one starting from A to which I've applied that time-dependent random gauge transformation. And even that identity should actually only hold in law, because when you do the, you know, the actual formal calculation to check that that identity holds, you find that one of them is that equation driven by, you know, the noise you started from, and the other one is basically the same equation but driven by the noise which you've conjugated by G. And then conjugation by G is an orthogonal operation, and so, you know, by E to isometry, that should be the same guy in law, right? So that's here the symmetry that this guy is supposed to satisfy, right? And now the question is, does it actually satisfy that symmetry, right? I mean, that, so you can construct the guy, right? So the general black box kind of theory of regularity structures tells you, well, if you mollify this guy, then you can add a bunch of counter terms in such a way that this equation has a limit, right? But it doesn't, the theory doesn't know anything about gauge invariance or anything like that, right? So it just gives you a cooking recipe of how to add counter terms. And here it turns out that the counter terms you end up adding are actually just of the form some constant times A, right? Now, the problem is that in order for that gauge symmetry to be satisfied, there had to be like very subtle cancellations in here. Like basically, if you replace this by basically anything else, these cancellations don't work. Right? So you add a term like this, it's going to break gauge invariance, right? In principle. But then on the other hand, it also relied on the fact that you had something like this E to isometry. It relied on the fact that if you conjugate this guy with G, then you get something which has the same law. That's true for white noise. It's not true for mollified white noise. Right? So you've kind of broken gauge invariance in two ways. So you've broken it because of the way you've mollified the noise, and you've broken it because you've added that term. And now the question is, in the limit as epsilon goes to 0, does it actually get restored? Right? So is the way you've broken it here and the way you've broken it here, do they just precisely cancel out in the limit so that you do actually have gauge invariance in the limit? Right? Okay, so what do you have to do? So now in principle, right, there's not much choice for that constant, right? I mean, it's like, if there's some choice of constant here that makes this thing converge, then basically the only thing you're allowed to do is add like an order 1 term to it, but you're not allowed to do anything else, right, if you want to have something convergent. And here the situation is a little bit like with phi-4 in the sense that this constant here, there's a 1 over epsilon contribution, which is relatively easy to describe, and then there's a log epsilon contribution, which is a pain. And unlike in phi-4, the log contribution is just one, like a sunset diagram or something. And so you kind of know there's one multiple integral that gives you that log contribution. Here, there's like 100 of them or something. I mean, literally. Right? So it's a log contribution, but it doesn't just come from one multiple integral. Like it's a sum of loads of them. And so it's essentially impossible to figure out what the prefactor of the log is. Right, because you've got like 100 of these diagrams and they sum up. Okay, I mean, if you can do the calculation without making any sort of mistake, you can figure out the prefactor, but I can't do that. So in some sense, you kind of know the form of that constant, but you don't know the actual expression for this constant. But you know that it exists. And the thing you also know, and that's what the sort of general theory tells you, is that there is a specific way of choosing that constant, which we sort of call the BPHZ renormalization because it's sort of analogous to BPHZ renormalization in field theory. But that one, it's not completely canonical because somewhere here it relies on a cutoff of the heat kernel, and that's always related to the fact that the logs, you can kind of add constant to the logs and you never really see the difference somehow, right? But basically, given a choice of cutoff of the heat kernel, there is a BPHZ renormalization procedure, if you want, that determines a choice of constant here. Of which you know that if you take that particular choice, there is a limit. And furthermore, you have really good stability properties of the limit in the sense that, you can put, like constants in front of things and everything is continuous in all the constants. Everything is sort of uniformly continuous over compacts in all of these constants. You can take different approximation procedures, like instead of just hitting the noise with a mollifier, you can hit the whole nonlinearity with a mollifier or something, and you know that you're going to get the same limit and so on, right? So you have very, very good stability properties of that, and that's sort of the key in the result. On the other hand, it's not canonical, right? So there's no reason why that particular choice of C should be the right one to get gauge invariance, because it relied actually on some cutoff of the heat kernel, which was completely arbitrary, right? If I choose a different cutoff, my BPHZ renormalization procedure would give me actually a different choice of constant. The only guarantee is that they differ by something that converges to a limit. It's a finite limit, which is non-zero, so right. But it gives me a way of somehow putting an origin in some sort of coordinate system somewhere, right? So that's the important thing. And so, okay. So now what do you actually want to do? So you want to say, on the one hand, right? So I want to show I want to ask myself, is there a way of choosing that constant so that this type of gauge invariance is actually satisfied, right? So what happens if I choose, right? So on the one hand, I can look at B equal to AG, and the G is the time-dependent G, which is sort of the correct time-dependent G. Okay, so I take the G, which satisfies whatever equation it's supposed to satisfy. And then the equation I get for B is, exactly the correct equation if you want, except that you end up with a G, right? So clearly that guy is going to end up conjugated with G because of, sort of A being conjugated with G here. And then there is this term here, right? So if it wasn't for this term here, the equation for B would just be that. But there is this term here, and the thing is that that one would basically just turn into that, but that's not B, right? B is actually that minus that. So this term is B plus this, right? So here you would actually end up with a minus C epsilon B, but then also minus the same C epsilon times dGg inverse, right? So you end up with something like this. So it's clearly a different equation. It's different in two ways, right? So on the one hand, this guy ends up conjugated with G, which in law is really different from this guy itself, because at fixed epsilon, that one doesn't have the isometry, and you have this extra term here. Right? On the other hand, what we can do is I can look at the BPHZ renormalization of the equation where I add this term with this conjugation with G to the right-hand side, right? So I can look at the BPHZ. So I look at B tilde, which is the BPHZ renormalization of the equation, like exactly the same equation as here, except that I actually put the G's in front of the noise sort of by hand. Right? So I take that as the equation that I'm renormalizing. Right? And if you do that, what you get is more or less the same. Now, there is a linear term which basically comes from the renormalization of the nonlinearity here, and that's the same as the equation I started from, and so that comes with exactly the same constant. And then there is another counter term that comes from these products with the G's, right? So now here there's more work involved in figuring out what sort of counter terms that produces, but if you go through the motions, what the theory spits out is that it produces precisely a counter term of that type. And it sort of tells you what the constant is in front of it. And you sort of see that it's more or less of the same type, but with different expressions, right? So it gives you some other constant, C epsilon tilde, times sort of dGg inverse. Okay? Now, this guy here, we actually know that it converges in law to the same as the BPHZ renormalization of the original equation. That's because of this stability of the BPHZ renormalization, which also tells us that, like conjugating with G, one way of doing it is we could have actually conjugated white noise with G and then hit it with a modifier, and we would have gotten the same limit because of these stability properties. But that one in law doesn't actually depend on G, and is just equal to the original guy. And so therefore this guy, a priori, we know that for the correct choice of renormalization constants, the ones given by our BPHZ theorem, that guy in law is going to have a limit which is the same as the limit of that guy, right? If I start from the same initial data. Whereas that guy, I don't, right? So that guy is the one that was sort of the gauge transformed, and I would like to show that that guy is the same in law, okay? So then the question is basically, you know, is C epsilon tilde equal to C epsilon, right? So for both of these, if you have like this BPHZ theorem, gives you explicit formulas for both of them, but they are not the same formula, right? They're different formulas. There's no reason a priori for these guys to be the same, and they're actually not, right? So they're really not the same. And now the claim is that what you actually have, and that's the main bit, so the theorem, if you want, is that C epsilon minus C epsilon tilde converges to some constant as epsilon goes to 0, right? So they are not the same, but they actually differ by something that has a limit. And I claim that that's good enough, because what I can do is I can say, aha, the actual equation I can sort of cheat. I can say, the equation that I wanted to renormalize was not actually Young-Mills. It's Young-Mills with an extra term, which is k times a. So, right? And then I can go through all the same motions, and I find that somewhere here I have like a k times b that gets added, whereas here, I don't know. I mean, one of them it sort of gets, right? So if it gets added differently for the two, and then I can just choose. Basically, if you choose k to be that k here, or maybe minus that k because I probably made a sign mistake, but if you choose the k in the right way, then the way it enters here is precisely in such a way that it kind of cancels out, and you end up with exactly the same thing, right? So if you know that, the claim is you're done. Right? And now, why is that true? Okay, why would it? So in principle, you have explicit expression, so you could sort of check it, but it's infeasible because you have a sum of log divergences. It's like it's a large sum of sort of many log divergences. You basically need to know that the prefactors of these log divergences that show up for that guy add up to exactly the same value as the prefactors of the log divergences for that guy, so that the order 1 bits are the only bit that differs, okay? And so the way the argument works is the trick is you assume that this goes to infinity, okay? So by contradictions. So actually, I'm going to just show that this remains bounded, okay? So you assume by contradiction that it goes to infinity. And now what you do is you use the fact, so you add a constant here in front of the noise. So now I have a family of equation with that constant, and I know how that constant sigma shows up in the renormalization constant, right? So like in front of the 1 over epsilon terms, there's going to be a sigma square. In front of the log divergence, there's going to be a sigma 4. Let's forget about the 1 over epsilon, guys. So let's just pretend there's a sigma 4 in front of this, okay? It makes no difference. So you end up with a sigma 4 here. And so now what I'm going to do is I'm going to choose the sigma epsilon in such a way, right? I'm going to choose the sigma as depending on epsilon in a way that goes to 0, and in such a way that sigma epsilon to the 4 times C epsilon minus C epsilon tilde converges to some constant. And what happens if you do that, then, okay, I'm running out of time. So I just tell you what happens, and can believe me that you can do that, but it's really not a difficult calculation to actually see what happens, right? So it would just sort of take maybe 10 more minutes to do it, so I don't have time to do it. But what actually happens if you make that particular choice, right? And you look at, you add this constant term here, then you use the fact that you have this stability of BPHC renormalization. So you actually know that this guy here, as epsilon goes to 0, really converges to the deterministic equation with this additional term here somehow. And you know the same thing. There's a similar kind of statement for the BPHC renormalization here, and there's a statement just because of continuity of applying the gauge transformation. And then what you actually end up having is you end up finding a contradiction, because what you find is that you just end up with the deterministic sort of like gradient flow for the Young-Mills theory, but you find a statement which sort of says that, I actually apply a gauge transformation to the gradient flow, and I find something which is not actually gauge equivalent to the gradient flow. But I know that the gradient flow is gauge invariant, right? And so that gives you actually a contradiction, right? And so since the only thing you've assumed here is that this guy blows up, so that I can find sigmas that go to 0. So it's important that the sigmas go to 0, because that's what gives me a deterministic limit that makes the noise kind of completely disappear, right? And so at the end of the day, well, so since that had to be wrong, it means that this difference actually has to remain bounded, right? So you get a kind of analytic statement about some cancellations between log divergences, which comes out of a completely kind of soft argument, right? And just about looking at something about sort of the limiting heat flow. And then you can actually run a sort of slightly different version of the same argument to show that the difference actually has to converge to a constant. Right? Like by compactness, there are subsequences that converge, and you can show that actually you get a similar contradiction if you assume that there are two different subsequences that converge to two different limits. Okay. So, okay, I think that's probably a good place to stop. Thank you very much.